All right. So let's continue our discussion here. So we have reached to this point. Let's look at one example. It says determine. So again, we are working on this WSD or ASD method, allowable stress design, working stress design, same thing. It says determine the bearing stress in extreme fiber. Is it going to crack? Is the concrete going to crack? It's talking about the concrete. All right. It is this moment, it is the apply moment. All right. This is a compressive strength of concrete. And you're dealing with normal weight concrete. All right. So if this is your cross section here, you're dealing with this cross section. All right. So first of all, when you're gonna crack, right? So if you think about it, when you are going to crack, when you are cracking, when you are reaching to the tensile strength. Why I'm saying this? Because if you remember, I told you the tensile strength of concrete all right, is much less than compressive strength. All right, so FT, F prime C. Okay, so if you reach to this FT, which is basically sort of like a weak point of concrete, you are going to crack. The concrete is going to crack, but that's a lower one. That's easier to reach. The load will reach to this strength faster. Does that make sense? All right. So this causes cracking first. So now you're understanding that the tensile side of the concrete or tension side of concrete will be cracked first. Of cross section, I can say, to have a better wording. Tension side of cross section will be cracked. Why? Because in overall tension is less than compression strength wise, and the load is going to reach to the lower one first. All right. So knowing this, now you know that it is important for you to realize how much is the tensile strength. All right. One way I introduced to you already was the modulus of rupture, FR. That's one way of estimation. All right. FR is 7.5 lambda F prime C. All right. So it is a normal weight concrete. So for that, lambda is equal to 1, right? F prime C, this problem giving you to be 4,000 PSI. All right. So if you plug in the numbers, FR would be 474 PSI. Okay. Now that you know this is your threshold, does that make sense if I tell you this is your threshold? So this is the amount, this FR, this is the amount of stress that if you reach to that, you're gonna crack. Sure, let's just write it. So this is the stress amount that the beam cracks. Okay, 474 PSI. All right, so now let's calculate. So you know your threshold. Now let's find your actual stress, and then we're gonna compare it. All right, what is your actual stress? So you know that this is a formula, remember from mechanics of materials, F or sigma, if you remember over there, we were showing the sigma, is my over I, bending stress, remember that? So moment of inertia, let's just find the moment of inertia of the system, all right? So moment of inertia of the system, if you want to be so meticulous, you would say, all right, there is a concrete section and there is a steel section. The system is not homogeneous, right? So you would say, all right, you need to convert this steel to concrete and then find the total moment of inertia, all right? But it is not necessary. We can simplify and say, all right, IG, the gross moment of inertia, gross moment of inertia. All right, only consider concrete, uncracked. All right. Why I'm saying this? We're gonna have a little bit explanation in the next slide. But in overall, we are assuming that all right, the steel is very small. Look at the area of a steel compared to the area of concrete in the section. The steel is very small amount. So we can ignore it and just safely say, all right, just moment of inertia, let's just assume the total moment of inertia because of the concrete only. So we assume everything is made of concrete. That's it. All right. So if you are good so far, I'm gonna erase the page and just continue writing on it. All right. So far we have found this FR here. Moment of inertia, you know that easily from, so you need to find it about the neutral axis, right? It would be what? It would be width times height to the power of 3 over 12. So 12 times 15, but don't forget 15 plus 3, right? Because the total height h is 18 inches. So 18 to the power of 3 over 2. I'm going to talk about that D concept right now. All right, so this would be your moment of inertia. All right, so before continuing, just quickly what's going on with that D concept here. All right. This D is effective depth. Effective depth. So this D really means that the height from top of your section to the level of reinforcement. Tension reinforcement. All right. So if I want to give a definition for it, I would say the depth between extreme compression fiber of concrete to tension steel. All right. So from the extreme fiber farthest away from the neutral axis on compression side to the tension steel level. All right. This is effective depth, D. And this 3 also, it is called a lot of times CC or just lowercase c. So this is in concrete, we call it, it's not quite there, but I'm gonna give you a name here, a little bit different it would be because we have more to add to this concept. We're gonna learn about it more, but it is called concrete cover, all right? So this is not exactly this 3 concrete cover, it would be whatever after steel left. So for example, for this case, concrete cover really would be this much, right? So I just wanted to give you a definition here since we're just talking about the cross section sort of different elements, all right? So concrete cover would be distance or the height between end of a steel and concrete edge. All right. Okay. So having this said, let's just continue with the stress here. So bending stress, what is the actual bending stress? Let's just find it. It would be my over I, right? Or mc over I. So it would be what? Would be the moment given to you. This is the applied moment, 25 kep foot, okay? So this 25 kep foot times 12 to make it kep inches and times 1,000 to make it pound inch. Y, a distance from the neutral axis, okay? So what would be the distance to the neutral axis? Let's see. So the total height is 18, right? So the half a height would be 9 inches, correct? So this is the Y really. It's captures from the neutral axis, if you remember from mechanics of materials. So this would be the Y concept, 9 inch. Moment of inertia, you have found it on top. This is the Y. Or if you remember, we call the C for the maximum distance from the neutral axis. All right. So your maximum bending stress would be 463. Okay. So the question is it going to crack or not? All right. So this value is your actual stress. Actual stress. Okay. Your actual stress is 463. Your limit to crack is 474. All right. So guess what? What's going to happen? Your actual stress hasn't reached to your limit. So you're safe. You're good. As soon as actually you reach to your limit, you're going to crack. Okay. So no, it wouldn't crack since your actual stress, actual bending stress is less than your limit of cracking. All right. So you wouldn't crack. All right. Let's go to the next slide. All right. So you realize that you wouldn't crack. But one question can be, all right, what is the cracking moment? So for the same problem that, all right, this was your original like applied moment given to you. This is a compressive string of concrete, right? 4,000. It was similar to the previous problem, right? Yeah. Okay. So on this problem, you realize that you wouldn't crack with this moment. But the question is, all right, what moment will crack it? What is a cracking moment now? All right. How we can answer this question? Let's look at it here again. So really what I'm saying here is that the applied stress, right? It has to be less or equal to your limit stress. Or I would say the strength that your material has. All right. So when it's gonna crack, so well, what would be the threshold for cracking? If these two become equal, that would be the threshold, that would be a starting point for cracking, right? So if I want to find what is the cracking moment, I can say, all right, so the cracking moment that I do not know, multiply by y over moment of inertia, gross moment of inertia, because I'm just using the whole concrete. So this is how to find the F actual. I'm making this to be equal to the FR. Does that make sense? The FR, which is the limited stress. Okay, so this is unknown. This is unknown at this point. Because this M25 is something I said, all right, don't care about this one anymore. I just want to know what moment causes to crack then, because I understood the 25 wouldn't crack it. All right, so if I want to find the MCR, what would I say? I would say MCR is equal to FR times IG over Y, right? Just like MCR is equal to these two guys, but times over Y. All right, that's what you see here. FR, this is a, we already know that, right? What was FR? If you remember, we found it from this expression. Okay. 474 psi, moment of inertia 5832, and y, which was really the distance from the neutral axis, was 9 inches. All right, so you just plug in everything here. This number would be in pound inch. But if you want to show it in terms of kept foot, just right at the bottom, you have 307,152 pound inch. All right. So if I want to make it in kept foot, so first of all, for the kept, you want to say 1 over 1,000 to make it in terms of kept. All right. Also multiply. So if you want to make it in terms of from inch to foot, you would say 1 over 12. Again, you're going to say inch and foot here. All right. So if you do that, 25.6 kept foot, you'll get. All right. So look at this. This is your cracking moment. Cracking moment. That is the moment you crack your system. So this 25 in the problem, it was below this number. That's why it didn't crack. All right. If it goes like 0.6 higher, that was gonna crack your cross section. All right. Did we talk about everything? All right. So quickly, let me review here that why we didn't use a transformed eye. Remember that about the concept I was talking about, all right, why we didn't think about the steel as a separate sort of another type of material, and then just like have a transformed moment of inertia. So the area of the reinforced steel as a percentage of the total or gross cross-sectional area of a member is quite small, usually less than 2%. And its effect on the member is almost negligible. All right. So number-wise, it wouldn't be. So this effect it's talking about is not about talking about the mechanical effect. It's talking about the number effect. Like when we are calculating the moment of inertia for like a big transform moment of inertia, it's talking about that. So it says that, all right, we don't, if we just assumed everything made of concrete, it would be very close, the very close answer. We don't have to be so meticulous there. That's it. When it is not cracked, do not forget that when we are talking about the edge of cracking, before cracking, and on the edge of cracking, we are using the IG. All right. So for uncracked beam, we are using gross moment of inertia. All right. Gross moment of inertia. Moment of inertia. If it is cracked though, we need to use transform moment of inertia. We need to take account for reinforcing steel. All right, so if it's gonna be cracked, the concrete will crack, that would be different story now. And over there, we need to use transform cross section. I'm gonna solve an example for this. All right, let's see what we are talking about. Let's see. Let me make sure that's problem. It's gonna crack. All right, so this is a good one. All right, so let me do something. I'm gonna erase this page. I'm gonna make a new, let's see.